So students, there's 2 downloads under the materials tab just above this video. And if you haven't already downloaded those, you might want to go ahead and do so. But the first table we're going to walk you through, you've already seen if you've read chapter 1 of the book, which was a few lessons ago. And it was this comparison between what I'm calling a resilient property versus most modern day design or most modern day approaches. And there are, I'd say, 5 characteristics that you can really identify quite easily and especially see the differences between a resilient design or a resilient system. And I'm going to, again, the words might be interchanged, but what is a system? A system is just a bunch of interdependent and interacting component parts forming a complete whole. And what is a property? When you think about somebody who might have built a house on a piece of land, there's tons of different interdependent and interconnected parts: the house, the water supply, the rain tank, the solar panels, the landscaping. All of these are just different parts of a whole. And so, and hence a resilient system or a resilient property, the characteristics could be applied interchangeably. They're, in a sense, principles. No matter what system you're looking at, you should be able to see these ideas quite evidently if that system is actually going to be resilient. So the first of which, and actually in no particular order, and maybe Peter will go through them, but perhaps there's some that are actually more important than others. But the first one I have here on the table is efficiency. And the sentence under a resilient property is that the focus is on maximizing efficiency versus modern day design. There's almost I'd say an unlimited resource mentality.
So that's really a limits to growth reality as well in your efficiency. So efficiency here doesn't necessarily mean economic rationalism and economic efficiency. It's efficiency in the face of scarce resources, which is really part of the resilience, a key part of the resilience conversation.
Right. And I see that, sometimes it's almost easier. There's so many more examples of modern day design around us, right? It's sometimes easier to understand the concept in seeing the antithesis, the opposite. And one of the major ones I see all around me is this energy and fossil fuel used to make up for design shortcomings, right? That one I feel you can easily find examples of that.
And it goes even further in modern day design. In my country, is use as much water as you like, because then we can build more desal plants, and so it's an unlimited resource, but that is not resilient because it actually produces a very large carbon footprint, and which is a circular process. So feedback loops are all about systems and resilience, which actually is affecting the way it rains and increasing temperatures and increasing water demands and reducing the availability of water. So you've got a feedback loop going on there of, it's an unlimited resource. Use as much as you like. Let's build more desal plants. Oh, sorry, they need more fossil fuels to run them. So your resilience and efficiency and this failure to understand that we have scarce resources is a very large feedback loop.
And tied a little bit to what you said yesterday around externalities not being accounted for, I'm suddenly thinking of applying this word efficiency to say to our industrial food system, which some might argue is a really efficient system, right? Is it an efficient use of resources to be, at least here we're in where I live in Canada, where most of our vegetable come from California, which is quite a ways away.
So that's quite a feedback loop, isn't it? Because what's hidden in that industrial food complex is some very large transport distances, which are, of course, energy intensive. And if the growth of that food is very dependent on artificial fertilizers, there's an entire feedback loop there. So when you're considering, say, as part of your home scale system of growing some of your own food versus buying it from the supermarket, which might appear to be cheaper and more efficient, there's an entire hidden set of feedback loops, the part of this resilience discussion that should be considered.
Mm-hmm. Mm-hmm. A few other the points there in the table, which I don't know if they need too much expanding on. I think, in efficient systems, the designs are enduring and repairable, solid state, low tech, often, not always, but often, versus in, this modern day fragile. I could even use the word fragile on the right hand side of the column in a lot of ways. I think low quality, disposable, planned obsolescence are the words that come to mind.
Yeah, and sustainable systems, resilient systems, actually, to a point, are self-renewing and they're reorganizing. So as you live with them, they become rearranged to better suit your changing lifestyle and your changing priorities and the changing world you live in. With the fixed linear traditional systems, they can't adapt, so they're not adaptable. So what you're aiming for in your discussion about resilience are systems that can more readily adapt.
Oh no, there should be adaptable somewhere in there. Because
There
you're
should
right, it's
be.
true. Yeah,
We're
adaptable would
getting
really
ready
be
to
a
think about these
characteristic.
issues.
Absolutely. Yeah. Yeah, and it's kind of also, I'd say adaptable things are quick. You can adapt quickly, they can shift quickly and move quickly versus really slow moving things. An example coming to mind is I recently read a book called Exponential Organizations, and it was a book about the old business model where these big giant corporations, right, were basically the corporations that were doing the best in the economy worldwide. And now we're at a place where it's all these small little swift software companies that are nimble and quick and able to adapt and see opportunities and try things out, right? So there's just an interesting another system um, example.
To use another evolving buzzword, they're agile because they're adaptable and flexible. Um, the world is changing rapidly and resources are scarce. So, um, and these smaller, um, more efficient, more adaptable entities are the ones that are more likely to survive, which is the opposite to the previous paradigm where big, centralized, rigid, hard, fast, reliable um, is not adaptable or flexible or resilient. So society's changing. So this is what our home scale design process is about.
Right, right. The next word, which is I think maybe one of my favorite, just a personal bias of mine, is this idea of being productive. That systems, um, yeah, that and in the opposite sense of just being consumptive, right? Where in my mind, that I picture that consumptive model where you've got just inputs coming in and outputs or excrement going out. Or for instance, the pinball machine. I love the old fashioned arcade pinball machine. Consumers are just constantly dropping pinballs into the top of their machine and then just letting them go straight through to sink, right? And making no points. And in kind of this resilient design or sustainable design or even permaculture design, I love the idea that we love to put in paddles. We really like to put in paddles and elements that we can actually start playing the pinball game and keep those balls in play longer, um, and find yields and be productive. Yeah.
Pinball wizard.
Yeah, I love it. I just love the analogy. I can picture all the pinballs, right? In one example, you're just putting in pinballs in the top, and they're falling through the bottom, bing, bing, bing. And the other one, you put one pinball, two pinballs in, and you play for 20, 30 minutes, right?
Right. So we're going to keep all the balls in the air and in the machine, and um,
All right. And the next row in the column is appropriateness. One that we see a lot here in my context is that many of our homes are heated with natural gas. And natural gas is a fuel that burns at, I believe, 2100 degrees centigrade. I mean, it's very hot, right? And so we can melt metal. There's just incredibly valuable things that we can do with such a high quality fuel source or high energy density fuel source. And yet, we really only want our homes to be about 21 degrees centigrade. And so it just seems like such a insane mismatch of energy density to our needs.
so it's a that sort of consideration is a hangover from when population was small compared to perceived availability of resources. So it didn't matter how inefficient our use of good resources was because there were few of us and lots of resources. We've actually changed that paradigm in the last 50 years and increasingly so in the last decade. So all resources are scarce now, so we have to find the best uses of them. And I think every one of your points, Michelle, is interrelated. So it's a system, isn't it? And it's resilient. Using the right resource in the right place for the purpose that you intend, appropriateness, is probably a key issue in the resilience discussion. And that using local water because it's available rather than having it run off your property and maybe do damage to someone else's property, and only using some of it rather than all of it. It's impossible to use all of it, rather than transporting water from maybe 200 kilometres away via lots of pumps and pipes and machinery and hard infrastructure that needs to be maintained and replaced. Is probably one of the key considerations about whether or not you harvest rainwater on your property.
Right. And wouldn't you also, another great rainwater example is um the the quality the quality that it needs to be treated compared to its end use and matching those up.
Yeah, and when people are talking about systems of resilience, they're often talking about magnitude, and there are new conversations now about quality. We have to do a lot to water and add something like 20 chemicals to water to make it safe through all of the pipes and infrastructure that can be compromised in all sorts of ways, including the materials they're made of, to get it to a house in some sort of safe form. There's all sorts of quality compromises to survive that process. When you're going the other way from rainwater harvesting, you've just got a fairly good quality available to you at your property, and you have to do less things, consider the treatment train, to actually produce the same quality outcome or potentially better. So this quality resilience is, and feedback loops is a really key issue.
And then let's talk a little bit about interconnectedness and why that's an important characteristic of a resilient system.
And it's probably important to note here, this is probably one of the areas which it's of resilience and systems that are affected by so many other buzzwords, joined up, linked, integrated, to name a few. So, Michelle, you're here talking about all of those same systems of
And I'm
how,
guilty. I'm guilty of using different words all the time.
but this is what we mean. We need to understand how things are joined together and how they influence each other, um, and the feedback loops that join these things together. So um, they're interconnected, are they not?
Absolutely. And you brought up feedback loops, which I've always known the importance of feedback, and I've seen it happen personally, just in terms of, having gotten a solar hot water system on our home and seen how it influenced our own behaviors and our own usage patterns. And the same can be said of, people who are on harvested rainwater or on stored water, right? It absolutely changes how much they use. Or, gray water. If you're using gray water on your home, it's almost guaranteed you're going to clean up the kinds of soaps or the kinds of chemicals you pour down the drain. And of course, gray water is would be assumed. Gray water would be any kind of water from your sinks and taps, your hand basins, that would be directed to landscape. Just to provide a definition of that if anyone doesn't know what that is. Um, and then recently, Peter, you recommended that I read Donella Meadows' book. What is it? Thinking in Systems. And I must say, if I were to write this book now, I think I would have another row called feedback, because she really harps on the importance of feedback, that it's critical. Hmm?
Everything we do in life is about feedbacks. You know,
Unless we design things to minimize or so that we don't see the feedback of our actions. No, I mean it is about feedback, but often uh, we don't see.
a key hidden design criteria is actually dealing with feedbacks, and it's not explicit in the way we mostly do our professional designs, but it's there in the background. And good sustainability designers, good resilient designers put the feedbacks um, and the feedback loops in their front of mind in their design. For instance, later on in your book, in this course, we're talking about, do you really need a massive size rainwater storage to cope with all eventualities? Or do you include the feedback loop of, it's a little bit drier, maybe the people, which happens in rural Australia, where people rely on rainwater as a sole source of water, where people say, hey, it's a bit drier, we'll all take shorter showers, or we'll manage our water differently, we'll behave differently because we now have a feedback of it's raining a bit less, or it's hotter for a while, and that's a feedback loop. Um,
Are many modern day designers or many modern ways of approaching design not, would you say they're not properly taking into account the influences of feedback on a system? Or
well, most professional design and analysis in water resources and economics, for example, are linear, um, siloed, and average. Um, they use average inputs, like average water use, rather than the distributed behaviour of people that might change the infrastructure. So,
well, because it's far simpler, right? It's much easier to say, we know, we took this city and we know that there's X million people and they use X million liters. So every person uses, divide the former by the latter and you have liters per person per day, right?
yeah, right. And it sounds really logical and reasonable. But my colleague Michael Barry and I just won the Alexander Medal science medal in Australia for proving those sorts of assumptions are completely unreliable for understanding the security and resilience and even the amount of infrastructure you need in a system, because it doesn't account for the local behaviours of people and businesses, and they respond differently depending on what's going on at different stages of their life, or whether it's hotter or drier, or whether there's an economic shock or not, or whether their income. There are so many different things. So basically, if you just using averages and just using linear analysis and siloed analysis is the other issue that we won the award for, where you're only analysing, say, the water pipe network. It tells you nothing about the rest of society if you're only putting an average water use in there. So as a consequence, you're not designing a resilient or a sustainable system ultimately, because if something changes from that very set of general assumptions you've made just to design a pipe network, it won't be adequate anymore. Or it could be so over-designed that it locks you into, as the economists call, crowds you out, if the costs are too high as well, from doing more sustainable and resilient things. So redundancy, feedbacks, including the natural variability and the human variability, is something we're talking about in this book, but it's not often done. But in the future, it will be. It will need to be.
And do you think that it's becoming easier to do with computational improved ability to compute things? Because it's also not simple to build models that account for behavioral changes in water usage over a whole city, for instance.
Yeah, well, yes and no. If you keep trying to build the traditional models to account for that, we've also proved that's impossible, and that's probably why it's not done. But if you change the way you think about it, it's surprisingly simple to account for these things, but not in the traditional trying to apply these real things that are going on in the system from the top down. And it was the same as Danilo Mehta's discovery in her last book. You need a bottom-up framework of systems thinking to do that. And then you don't need many parameters. It's not really that hard. So sometimes it's just context and order of actions, which is also a key part of feedback loops and resilience. What is the best order of actions to actually produce the outcome that you need? So sometimes you might not even change the components in something in building or something you're analysing, but you put the components in your analysis or in your design in the right order, and it becomes far more sustainable or resilient. But sometimes, including this local detail is very simple. Some of this simplicity might have been overlooked, and we'll visit that during this course.
Right on. Well, what I'll say perhaps is, if we've inspired some interest in these concepts, these ideas of systems thinking, Peter and I will include some additional resources and some further reading that you can dive into, because it's a fascinating and really important, really, really important concepts and work.